Hello.
So what the demographics branching out into why does the next one design? I know it varies from year to year.
No, mostly it's computer science. Mostly.
Mostly.
Computer science.
Sorry, I didn't get. No, I know one year was the only one in physics, but it was a very unique person.
It's only that order of that one.
Huh?
2-3 people, 2-3. Oh, you're not.
Unless you're a planning.
Will we start? Hello, everybody. Welcome to another ICTS String seminar today. We have Alok Laddha from Chennai who's going to tell us about positive geometries and S matrices or scalar field theories. Oh, a short announcement. For those people who are joining online, please feel free to unmute yourself and just ask questions whenever you may have.
I'll start. Okay, thanks. Now for the invitation. So I'll just give you an overview of some of the work we have been doing, understanding the S matrix of quantum field theory from geometric perspective. Most of what I will say is based on work with my friend Brunmai, who was at CMI and now he's a student at Caltech. So I'll give you basically it's a program. So I'll try to give an overview of the program and some of the recent results we have obtained, but feel free to ask me questions at any stage. So the basic idea of this program starts from a very generic question is that, given a space of external data, so just to be very concrete, let's say the space of Mandelstam invariants, for example. So if you look at scalar field theories, then we know all the S matrices are functions of Mandelstam invariant. So let's just think of looking at scalar fields, S matrix of scalar fields. So that question really we are interested in, which is the ultimate question which underlies this program, is that given a space of external data like Mandelstam invariants, how do we classify functions which can qualify as a S matrix of a local and a unitary quantum field theory as a S matrix, or more precisely because we are looking at functions, amplitudes, scattering amplitudes of QFT, local and unitary QFT. So that's the sort of the main goal behind this program, and we are seeing interesting evidence that the one way to approach this is in the following way: is that there is a class of there is an answer we are going to seek for this question, which is going to follow the following logic: that there is a geometry. There are a class of geometries. I will be more specific about what I mean, which are such that it has boundaries of all codimensions. I'll give you a specific example, and most of our talk will be about understanding these geometries. And it's such that once you find these geometries inside this kinematic space of external data, these geometries naturally come with some forms, which are called canonical forms. So all we have to do is, once we find these geometries in our space of external data, they come naturally equipped with some forms of different rank, like top forms or lower forms, for example. And these forms basically generate S matrix of some theories, some local and unitary theory. This is the sort of the we are seeing more and more evidence of this program, and so that's the sort of the classification scheme that we are going to follow and see how far we can go in this program. So I'll give you 3 examples which are now known for many years. One is the geometry called the amplituhedron.
Is that the arbitrary loop level? Is that right?
Arbitrary
Loop level?
Oh, sorry, I will say that. So right now this will be, I apologize, I should have said that. So the question is for to find, of course, the S matrix at arbitrary loop level, but the progress we have made is concrete progress is at 3 and 1 loop integrand level.
At the integrand level?
It's the integrand level.
But arbitrary loops?
No, 1 loop.
1 loop, I see.
1 loop. So far the program, but except in the n equal to 4 super Young-Mills were arbitrary loop. So there is one class of theories for which we understand this program up to arbitrary loop, but for we will see that the scalar field theory we understand it up to 1 loop at the level of integrand.
Okay.
So the first geometry of this type which was discovered, which motivated actually understanding, looking at this question in this light, was a geometry called amplituhedron, which is a geometry. It's a complicated geometry. We will not go into detail. I will just give it as an example, which lives in the external data, which are not Mandelstam invariants, but what are called momentum twistors. And this geometry is actually labeled by 3 parameters. I will explain what this means. So there are 3 numbers which kind of label this geometry, and it comes equipped with some form. And we know that this form corresponds to S matrix of, sorry, I should say S matrix integrand, as Ashok asked, of M loop amplitude at S matrix integrand at M loop for n to the k MHV configuration. N to the k MHV configuration. N is the number of particles, and so this corresponds to S matrix integrand at M loop for the specific configuration of external data in n equal to 4 super Young-Mills. What is? MHV is maximal helicity violating. So you have, in the case of gluons, you have 2 gluons with negative helicity, all the rest with positive helicity or vice versa. And that is MHV. And when you say n to the k MHV means you have k gluons with negative helicity and the rest with. So, yeah, okay, I will do that. Yeah. So this was the first remarkable result that was obtained in super Young-Mills, and from 2000, roughly 2010 or so, and now it has been understood in a fantastic detail, and many other connections of this geometry with amplitudes have been discovered now. But now, in recent last 6 years, we have also understood that this thing, this way of understanding S matrix extends to simple quantum field theories. For example, there is a geometry which we will understand in detail. Say that again. Over the loop momenta. Yeah. So then there is another geometry, and now this geometry is interesting and which will be focus of our talk. It lies really in the space of Mandelstam invariants. Which are Sijs. And it comes with its own, so you find this geometry. I will explain what this geometry. It's like a polytope. You find it. All you have to do is look for it in this Mandelstam space. Once you find it, it comes with its own form of. So this n-3 is the dimension of this polytope, and then once you find it, it comes naturally equipped with a form of the same rank. And it turns out that this form is same as the tree-level S matrix of phi cube theory, where phi has some color degrees of freedom. the details of this scalar will not be important for us. I'm not going into the very specific detail, but think of it as, if you are computing gluon amplitude, then the gluons have color, and this scalar is like a spin zero gluon if you want. So it has some color degrees of freedom. And so this just naturally comes out that if you find this geometry, then there is a form, and that form just produces for you this S matrix of the theory. So this was like a second data point that people discovered, and it was encouraging because it is not in the context of some exotic momentum twister space or anything. It's in this very ordinary Mandelstam space. And now we have understood that actually this extends to a large class of such theories when scalars have color. In particular, there is an entire family of such geometries. So I'll just indicate them as AC, which are called accordiahedra. I mean, so these geometries are discovered by mathematicians, but physicists, especially Nima and his group, realized that these abstract geometries, once you locate them in the Mandelstam space, they contain information about the amplitudes. And so there is another class of geometries. These are called accordiahedra. They again come with some form. And so once you find these geometries, you evaluate this form, and it turns out that they always seem to give you tree-level S matrix for some phi to the k theory, where phi has color. So roughly speaking, at the tree level, I will go to one loop in a later part of the talk. At tree level, this is the thing that we understood up to like 2 years back. That so we have a very limited zeroth order. I mean, so that's why we are trying to answer this question, and we see that this seems like a right track to go, where we are saying that how do we classify functions? Don't look for functions, look for forms in the Mandelstam space. And what forms you should look for? Those which come from some specific class of geometries. So once you find these geometries, and once you find the corresponding form, then they seem to generate S matrix of some theory. So it's we are really going, we are not starting from a theory and finding these things, we are going in opposite direction. So, yes.
How does this program getting the S matrix in the end, it shows that the S matrix should be unitary and
yeah, I was about to come to that. So that's a fantastic question. So obviously the point is that once you do this, why is it's a puzzle? Why is it that these forms produce for us local and unitary tree-level S matrices? And the entire secret of that lies in the details of this geometry. So these geometries are such that, I will explain this in more detail, but basically these things are such that they have boundaries. And if you go to the boundaries, then the boundaries are always product of lower dimensional such same class of geometries, which should tell you that it is like how unitarity tells you that any amplitude breaks into lower point amplitudes. So the way unitarity emerges is all completely because of the details of these geometries. And the way locality emerges is because these forms are meromorphic. So they have simple poles. And so that's why we get local amplitudes. Yeah.
Space-time dimension, 3+1?
So at this point, we are at tree-level amplitudes are totally agnostic. We are scalars. And so it can be any dimension. But I should say that in some sense, for technical reasons, otherwise things become very, very messy, we are in dimension larger than number of particles. So if you want, we are in infinite dimension because n can be arbitrary. Otherwise, we have to, otherwise this space of Mandelstam becomes complicated. That's the reason. Yeah, that's what we are finding, that, so suppose I didn't know anything about, I found this geometry, motivated by this first data point. I found this geometry in Mandelstam space. I evaluated the form. It seems to give S matrix of some theory where the scalars always have color. And what this color means is that these are what are called planar amplitudes. I mean, that's where the secret lies. That these are amplitudes which where if you draw the Feynman diagrams, you can always draw them on a plane. So now yeah. Say that again. Yeah. Does it not work means like, will you so yeah, maybe if I have time, I will tell you how, once we know this geometry in Mandelstam space, we can try to find what this geometry will look like in momentum twister. It looks very, very complicated. But that is part of the talk that, I mean, at least what I'm telling you will directly connect it to the question you're asking. So right now what we are saying is that look, why go to all these things for ordinary quantum field theories? We always work with Mandelstam. So if this program is the right way to classify S matrix, we should look for geometries inside the space of Mandelstam.
So once you have the approach with color,
Yeah.
you can always reproduce the approach without color, right? By setting, just ignoring color factors altogether.
Yes, you're right. I mean, but this form is always going to give us sum over planar graphs.
Yeah, but at a tree level, at least that's not the problem.
So you can sum over all these forms. Absolutely, you're right. But I'm saying that like what it gives first, like is a planar contribution. But you are saying you can sum over all the planar contribution in some way. You are right. That we could be there. But the geometry itself doesn't produce that. It produces planar. Yeah. So now, so motivated by these structures, we want to ask a question in more general, that which is also tied to what Ashok is asking. Is that so? There are two questions we would like to ask. One is like a bootstrap question. Which is that how do I know that if I give you so all these geometries have one feature in common, that they all have, if they all have boundaries of all 4 dimensions. And so there is a name for this. I mean, not a big deal. They are called positive geometries. So just to give an example of what positive geometry is, so if I take a segment, it's a one-dimensional line and it has boundary of dimension 0, so it is a positive geometry. But if I take a disk, so this is a positive geometry, but this doesn't have a 0-dimensional boundary, so this is not a positive geometry. This is some common feature that we find with all these geometries. And so then the question that we really want to ask is that if we find any positive geometry in Mandelstam space, in the space of external data, so I will denote the space of Mandelstam as Kn for n particles. So Kn is just a space which is coordinatized by all the Mandelstam invariants Sijs. So if I look at, so the question that we really want to ask is, if I find any positive geometry here and evaluate its corresponding form, do I always get some S matrix? Some tree level S matrix. That's first question. That's more of a bootstrap question, that let's start looking at all the positive geometries that mathematicians find and let's start drawing them in the Mandelstam space and then see whether they give us S matrix. And then there is of course a reverse question of this, which is that given a Lagrangian, so I will give you a specific example. So for example, if I take a Lagrangian which is so suppose I have 2 scalar fields, not one, which have different masses. And then let's say we have, suppose I give you a Lagrangian like this, and I look at its tree level S matrix. Is there a positive geometry that can produce the tree level S matrix of this kind of theories, where phi1 is, let's say just for simplicity, phi1 is massless and phi2 is massive? Yeah. I will. Yeah, think of this all still as a motivation. So 3-dimensional positive geometry is, we can have many positive geometries. Like one example would be, take a cube. Cube is a positive geometry because it has boundaries of all codimension. Means like we have a surface, we have an edge, and we have a vertex. Yeah, but it's not. If I draw a cube, then it's a linear geometry, right? It's not S2. Topological S2, I agree, but if I draw it in Cartesian space, it's not S2. It's described by linear equations, right? The boundaries are the face, the edge, and the vertex.
Can you also add derivative terms here?
That is the that is the I was going to come to the end. Our hope is that what the progress we have made in understanding these kind of theories, we may be able to understand, which we don't right now, how to get, say, nonlinear sigma model S matrix. But we don't have an answer. But I will tell you in the end why we think that there is some possibility that we get. Okay, so this is these two questions are our kind of rough motivation. Both are like inverse questions of each other. Yeah, any questions?
Hi, Alok. I have a question.
Yes, yeah.
It's a vague question, but since you know how to get amplitudes of phi cube theory,
yeah,
and the Lagrangian you have written down, if I write phi1 plus phi2 cubed,
yes,
then I sort of generate terms which look like this, right? Phi1 cubed and phi1 squared phi2.
Yes.
So can I somehow use the answer that you know for phi1 plus phi2 cubed to get amplitudes for this theory, to get the geometry for this theory?
But phi1 plus phi2 cube is not the same as phi1 cube, no?
No, I'm saying the terms that you've written down, like phi1 cubed, phi1 squared, phi2, and so on. You can think of them as being generated from phi1 plus phi2 whole cube.
Yeah. I was just giving an example. In principle, you're right. I could add a term which is lambda 3 phi1 phi2 square and lambda 4. I mean, I would not want to keep phi1 plus phi2 cube, but the coupling are too constrained. Like I want to keep couplings arbitrary.
Yeah. So like lambda 1 phi1 plus lambda 2 phi2 sort of.
Yeah. But not even that. I mean, I want to keep all the 4 arbitrary.
You want to keep all the 4 arbitrary.
So
right.
An example that the one that I will try to discuss in this is this particular one. But with Mrunmay, we looked at much more complicated Lagrangians and tried to find polytopes give us.
So I was generally my question was more like if you knew the geometry corresponding to some interaction and the geometry corresponding to some other interaction, and if I wanted to know, if I wanted to sum up the two interactions, can I also have some knowledge of how the geometries will add to each other or something like that? Right?
There is a specific notion called Minkowski sum of these geometries. So if I give you a phi cube and phi 4, then you could look at the if I just look at lambda phi cube plus phi 4, for example, then I like add these two geometries and obtain the amplitude.
Oh, nice. Okay.
Yeah. So, but you are right. So that is all part of this class of Lagrangians. I just give a very specific, just for concreteness, one Lagrangian, but we could look at much more complicated ones. In fact, as we will try to see that if you follow question 1 and try to first find positive geometry and then try to write the amplitudes, you get amplitudes for Lagrangians which are very, very complicated. So I won't have time, but just because they're asking, like we found that you could have some we found geometries which generated amplitudes for where each phi I has a different mass. So and then minus some like this kind of Lagrangian. We found geometries which gave tree-level S matrices for this kind of Lagrangians, but such that these lambdas were not always independent. Like there were some specific constraints among them. So if we follow the route of question 1, we found some interesting S matrix for some. I mean, not physically interesting, but some exotic Lagrangians. But so
I see.
Yeah.
For arbitrary lambda, you want to find.
We haven't found one yet. I mean, the hope would be to find for any lambda. But if we just follow our nose that you first find the geometry and see whether it gives S matrix, there are a class of geometries we find more, easily as Once we know this, we find them relatively easily. As you will see what I mean by relatively easily, which seems to produce this, where these lambdas are not independent, but they have some specific relation.
And one more question, Alok. You said that you'll be working with D greater than N, right? This is because if you had N less than D, then there are relations between the Mandelstam.
Yeah. Then it's a much more complicated thing.
Right. So in the
Chandramauli's question about the momentum twister. So yeah.
Right. So in the case of this N equal to 4 SYM, also do they know how to do N less than D, or?
No, because they are already with momentum twisters. So they're already
So there they know.
been taken care of. Yeah.
Right. Okay. Thanks.
D level, if you know the answer for D larger.
Yeah. In that sense, you know.
Yeah.
Of course. But
It
if you
answer for all D, right?
Yeah,
there
absolutely.
Some SIJs are related.
Exactly. Yeah, exactly. But if the the dimension of the kinematic space is it's totally unconstrained if your D is larger than
As if the SIJs are all in.
independent. Yeah, that's the thing. But in the end, once you get the form, you could in some sense continue to any D for scalars. Yeah. So now I will explain to you what. So let me first give you the result of which encapsulates somehow whatever little Mrunmayya understood about both these questions. And hi Loga.
This kind of mathematically natural fine theory,
Yeah.
we know like if you like some one loop computations.
Yeah.
Where these relations are preserved or something. Is there some nice reason why?
Yeah. So actually, what we have understood now is that we have found. Here I'm focusing on tree level, but we have found positive geometries which give one loop integrand for this class of theories. But again, the simplest one we find are those where these couplings are not independent. They have some constraints among them. Yeah. Oh wow, that I don't know. That's a great question. Yeah, absolutely. Yeah, it's not clear. You're right. Because they are not coming from some gauge, right? I mean, we are just imposing them. So I don't know if those theories are physically consistent once we do the absolutely. Yeah, that's a really good question, because here another problem is that here, not a problem, but of course this is always a property of positive geometries that we always find integrands. The loop integrands, not the integral themselves. So once we integrate, you're right. I mean, that's a very good question. No, not difficult. It's just that we haven't done it. But you're right.
The point is, you are working at arbitrary D, large enough D.
Yeah.
Generate all parts of phi one.
Yeah.
At loop, right?
Yeah.
So it probably is not invariant under RG flow anyway.
But if you do just one loop computation for some fixed n, he's saying, I think.
Yeah,
right?
but suppose you start with phi cube, right? You will probably generate phi 4 coupling at one loop.
Yeah, but I thought he was saying just focus on these terms first. Right?
You don't worry about phi 4.
Because there are constraints among these, whether the renormalized couplings respect those constraints or not. I think that was Loga's question. Yeah. No, you're right. Yeah. I mean, this was just in some sense, I would say, a little bit of a surprise that we found we couldn't, So at tree level, for reasons that I will explain, right now we are in dimension D larger than number of particles. But that is just a technical reason, because if D is less than or equal to n, then Mandelstams are not invariant. They satisfy these horrible Gram constraints, nonlinear constraints. And imposing them is, if you impose them, it is as good as you go to this space. So, right now I just want to avoid that. So we are just working with that.
But I don't know. I mean, you can always choose to express something in terms of the number of variables which is larger than the independent variables, right?
Say that again. So we are given the space. Let me explain the construction, because we are given the space of Mandelstams. Now the question is that if that's the way we are going to realize this polytope, is going to think of this as a Cartesian space, where all the SIJs are independent of each other. So that technically that is important for us, important ingredient for us.
Yeah. But I'm saying once you get that result.
Right? Yeah, absolutely. That I agree.
That's still a valid result. Even
exactly.
In arbitrary.
Right? Yeah.
Even in D equal to 3 or.
Yeah, but the geometry itself, that is not sitting in a kinematic space, which is a kinematic space for 4-dimensional Mandelstam. That's all. Yeah. The final form formally is obviously, as you are saying, the amplitude in any dimension, tree level, any scalars anyway. So. Yeah.
Following up on what I asked. So if you are, for example, working in dimension greater than 5,
Yeah. Yeah.
So, question is whether the geometry would know.
Yeah, that's whether inconsistency in the quantum field theory, but these are tree level, so I don't know if no, but you are right that once if we had, of course, the motivated from the amplitude hidden program, if the hope is that if we do understand positive geometry for the, so I should say a little bit more about this, that here the story was a little bit opposite, that first one found a geometry for the integrated amplitudes. And then one saw that, but actually the geometric structure was richer and it extended to the integrons itself. So that story kind of went opposite. But here we don't know whether the integrated answers have a geometric structure in themselves. But yeah.
About this program, can you say this program beyond positive geometric? We can think that positive geometries can be, for example, if you take an polygon and regular polygon and it will create this or
Yeah.
So can we just take this program for positive geometries and kind of continue it to the non-positive geometries also?
They are also positive geometries. We don't know whether the mathematicians have found, actually one also gave a talk last year in ICTS in a conference, these are called continuous associahedron. So if you take n to infinity and in a very specific way, you get a infinite dimensional polytope whose any n dimensional cut is an n dimensional associahedron. So there is a, but we don't know right now if that continuous associahedron, in what sense it is encapsulating S matrix of quantum field theory. But the object is still a positive geometry if you do the limit in a careful way.
But over here you said that the circle is not
Yeah, it's not a circle. It still remains a positive geometry. So the intuition that you are giving, somehow the way, I mean, of course it depends how you take the limit, but the limit, it's such that even if you take n to infinity, somehow you don't, the cusps you don't, like you keep them somehow. So it's a polytope which lies itself in infinite dimension. So that's the difference. Like I think you want to realize n going to infinity is still in a 2 dimension, but that polytope itself extends to infinite dimension. Okay, so I will first explain so this is the, sorry, let me first summarize the main result actually here, which is actually a nice surprise that there is actually, it may seem like we are finding different geometries for different theories and it little bit seems a bit ad hoc in that sense, but finally what we understand is so far that everything comes from one positive geometry, that is called associahedron. So I will write the answer first and then discuss some evidence of this answer, that all these theories, their amplitudes are related to a single positive geometry. So there is one, there is a single positive geometry called the associahedron. And you can realize them in the, you can draw them in this kinematic space. Variety of ways that we will see. So, so this is called realization because as you will see, this is some combinatorial geometry, it's some abstract geometry just defined by relations among different vertices. But once we can draw it, and what is remarkable is that mathematicians have taught us how to draw it without any other extra input coming from anything else. And if we exploit the realizations that mathematicians give us, there are many, and each realization gives us amplitude for scalar theories with cubic couplings. In other words, if I look at this example, and if I restricted myself, where I just look at different, I mean, I have like m species of scalar fields. I look at all possible interactions of the type then the S matrix of this theory and this theory, they both come from a same positive geometry, which is called an associahedron. But this associahedron can be realized, as we will see, can be drawn in kinematic space in many ways, and each way of drawing seems to give S matrix of some theory with cubic coupling. And if you now, I will explain, if you project it, there is a specific thing called projection, where you project this associahedron into the boundary, on any one of its boundary. That projection is also a positive geometry, always a positive geometry. And that seems to give S matrix of higher, 5 to the k theories. So the main result that I will try to convince you, at least first 3 level, and then if I have time, I will go to one loop integrands, is that there is a universality to these structures, that we have one positive geometry, and the different realizations give us S matrix of different scalar theory with cubic couplings, and their projections, as I have explained, onto different boundaries give us S matrix of 5 to the k theory, where k is larger than 3. So this is the main sort of the summary of the program that we understand so far for tree level S matrix for scalar field theories. So I hope to at least
understand the positive geometry. So you are saying, from what you have said so far, it's like you take a Cartesian Euclidean space.
yes.
Say any subspace bounded by 2-dimensional linear subspaces. That's a positive geometry.
Yes.
That's how it is.
Yes, because it has boundary of all codimension. Yeah.
Only things like the rounded are not possible.
Yeah, or you can have things which there is things which have no.
Special case. I can imagine that
Yeah.
very special case where there is no certain 4-dimension boundaries.
Yeah.
But generically, it will always have.
Yeah. Well, I mean, but you could. Disk is quite generic.
That's what I say. It's not a linear. It's not bounded by linear subspace.
Yeah, that's true. Yeah.
It's bound by linear subspace.
Yeah, but you can have positive geometry which are not necessarily linear also.
Oh,
Yeah, that's true. But positive geometries are much more general. So one example of positive geometry is the tree level moduli space, the worldsheet moduli space. So n punctured Riemann sphere, if you compactify, that is a associahedron. Actually, this is the same positive geometry, but it's not linear.
So you call that this input of point and declare that to point.
Yeah, then it's a positive. It's a positive geometry. So now I will explain in some sense the input up to here, and this is in some sense the power of this program, that this step as well as this step knows nothing about physics. I mean, this is something that mathematicians teach us, and that is why this thing is a little bit surprising, that from completely independent configuration there are some canonical ways to draw these polytopes, and they seem to have something to do with physics. And so that's where somehow the appeal to this, in my opinion, program also lies. I mean, it's not like we are necessarily engineering some geometries because we know the answer. The geometries are given for some other considerations altogether, but they give us S matrices of quantum field theory. So it tells us that maybe there is some deep link between these structures, match structures, and physics of unitary quantum field theories. So now I will explain the basic ideas of this construction. So let me first tell you what this positive geometry associahedron is, which is not very hard to understand. It's a simple combinatorial object. So the way to understand associahedron, you can forget physics for 2 minutes because it is just some combinatorics, and it's very simple. Let's take a simple example. So let's take a foregone, and let me just label the vertices clockwise. But that's not important. You can also label them counterclockwise. And now let's look at all possible triangulations of this foregone. And of course, there are only 2. So think of this now as a geometry where this vertex is this triangulation, this vertex is this triangulation, and the edge is no triangulation, empty triangulation. This is a one-dimensional associahedron. This object. Just give one more example. If we take a 5-gon instead of a 4-gon and draw all possible triangulations, then things are a little more interesting. So again, let me just label the vertices like this. And now I start with this triangulation, and then I want to look at other triangulation, but how do I declare a relation? Let me keep one chord fixed, then I have only one choice. This can go to this one. So I got another triangulation. Then if I go the other way, I would have kept this one fixed. And then I would have drawn this one. Then I'll get two more. So I just for completeness, I'll draw it. And I have so you see that and this is no triangulation. So each edge is partial triangulation in the sense that see which chords are common. So 1, 3 is not common between these two, but 3, 5 is common. So this edge is labeled by not a complete triangulation, but just one triangle and one quadrilateral, which is called partial triangulation. So each vertex is labeled by a full triangulation. Each edge is labeled by a partial triangulation where we remove one edge, and then if you remove one more edge, you get no triangulation, which is this geometry itself. So this geometry is two-dimensional associahedron. So of course nothing to do with physics right now, it's just some abstract objects. But of course you would see that it has something to do with physics, because you can see that there's a one-to-one map between cubic Feynman graphs and these geometries, because every triangulation is so this is not just to get an intuition. This is not something we use in our program, but just to get an intuition of why we should look at these things in the first place. It's very natural if you think about it, because each triangulation is dual to a cubic graph. Yeah. Yeah.
With the common triangulation, but it's possible that I have 3 edges inside this polygon, right? Then I could have drawn 2 edges.
Exactly.
So
that will be the. So if you have 3 edges, it will be a 3. So if I start with 6 gone, then I have each vertex is a 3 edges. Then I delete one edge, I get a 2-dimensional boundary.
Oh, I see. And then each edge would be labeled by 2 common.
And if I remove 2 edges, I will get 1-dimensional boundary. So if you remove k edges, you get a codimension k boundary. Okay, that's the. So what is remarkable is that this is true for any n. Like this construction, I'm just giving an example, but this was shown long back by Jim Stashev that you can do this at any n, and you get a consistent closed geometry of this type for any n, where you can glue with this rule, you can glue the triangulations together and you get this. And physically, if you think why we are doing this, why we are looking at these objects is simply because they have seem to have something to do with Feynman graphs. So that's the reason. Yes. So now the point is that yes. So thank you. So there's a counting now that if you start with 4 gone, you got a 1-dimensional associahedron. 5 gone gave you a 2-dimensional associahedron, which means if you start with a n gone, which intuitively corresponds to Feynman graph with n particles, that will give us an n-minus 3-dimensional associahedron, which we denote as a n-minus 3. Yes, the definition of this geometry is that we don't allow the chords to intersect. Yeah. There are interesting positive geometries you get if you allow edges to intersect, but we don't know if they play any role in physics yet.
And we always start with a planar object, meaning like this?
No, right now it's just an abstract thing. So, exactly. So we are starting just with, we are not starting with anything. This is just a math object.
But that one is a plane, right?
Yeah, everything is
all polygons on a plane.
All these abstract polygons which have nothing to do with physics are in a plane.
Are in a plane, okay.
Yes.
That's part of the definition of associahedron, or
that's part of the definition of associahedron, yes. That every vertex of associahedron is a complete triangulation of some planar n1.
And these can be generalized, or it's not?
Generalized means?
Not planar n1, but You go to
But when you say not planar means you will just change the ordering of this. Is that what you mean, or sorry?
no,
Not,
no.
Oh, you are saying don't triangulate two-dimensional polygon, like dissect higher dimensional
Yeah.
polygon. Yeah, in math, yes, there are some objects called matroid polytopes, but we don't know in physics if they play any role so far. Oh, that's a fantastic question. So for one loop, so this will give us some positive geometry, which will give us S matrix for tree level. But you could ask that, can I follow? Now that you're asking, I was going to come to it later, but you could have asked the following question. What if I dissect? What if I take a foregone, but I put a hole? That's what you are asking. And what if I look at all possible triangulations of this with a hole? That gives us positive geometry, which is actually, this will give a positive geometry, which is two-dimensional. And that gives the one loop integrand for phi cube theory with just a propagator. So yeah, I could say a little bit more. I mean, so yeah. Anyway, I will come to that. So if you how would we triangulate it? We could have done it like this. We could take this thing, or we could have done this thing, or we could have done this thing, or we could have done this thing. And then this combinatorial polytope, if you actually draw them in the Mandelstam space and look at the form, it gives us the one loop integrand for phi cube. So I'll come to this later. So these polytopes that I'm drawing now, strictly speaking, they are discovered by physicists, actually, Nima and collaborators, whereas these ones are of course known and they were discovered by mathematicians long back. And what is amazing is that even in last few years, there is a lot of development in which we will not go into representation theory of quiver. So I will just say some words, just that if people are interested, they can study this. I mean, so given, if I look at this triangulation, there is a natural linear quiver associated to this of the following type, that I put a dot here and I put a dot here, and then you see that these two chords are associated by an edge like this. And this structure itself is called a A1 quiver. I'm just mentioning this for people who may be interested. And based on representation theory of these quivers, mathematicians have found how to draw these in Cartesian space, how to draw these geometries in Cartesian space. This is an untrivial statement in the sense that if I give you this one-dimensional associahedron and I tell you draw it in plane, there are of course infinitely many ways to draw it, right? I'm just drawing a segment with two vertices. But everything I draw has an external input. I'm telling what the slope is and where the, what is it called, the intersection are with the axis. But is there a way to draw it so that the slope and the intersection is governed by some intrinsic object associated to this triangulation? That's what mathematicians ask. And what they find is that there is a unique way to draw this in Cartesian space if you don't use any extra input, and that is the following. That so if I take one-dimensional associahedron, if you don't, I don't give you any slope or anything, I just want to use the combinatorics of this to determine the slope, then it gives me a unique way to draw this, and it's this realize. So this is what is called a realization of one-dimensional associahedron. Realization just means we are drawing it, but the fact that we get this and we do not get this, comes from the fact that we are, the slope is dictated by some internal combinatorics of this stuff, and not if I draw it like this, means I am giving you some alpha beta. I hope that thing is clear. So now, of course, so the mathematicians tell you that this is the way to realize it, but we don't know if this has anything to do with physics. And what is remarkable is that this seems to have something to do with S matrix. So that I will try to explain.
Integer or rational numbers, right?
No, so I'm saying that if you just follow the realization coming from this connection with representation theory, alpha beta is 1, 1.
Only, no, here. I'm saying in general,
yeah,
right? these are always rational numbers because to begin with, you didn't have any continuous parameter, right? Those diagrams didn't have a continuous parameter.
No, I'm saying if I just give you this object, I can just draw it in any way I want in a plane.
No, I agree. But and you said alpha. So I'm saying in general,
Yeah.
these analogs of these alpha betas will always be rational numbers.
No. It can be anything, right? In general, I just give you a line with 2 segments. I can draw it in any way I want in a plane.
No, you can. But it's the ones which come from.
No, but like this is the associahedron. This object is the associahedron. It doesn't matter where it is. It is associahedron. Just a line with 2 vertices.
Yeah.
Now I can draw it in infinitely many ways in a plane with irrational slopes also. Doesn't matter.
I agree. Let's take the other example.
Yeah, other example also.
So here, when you draw,
Yeah.
is it always rational numbers?
Exactly. No. It's it can be anything, right? Because it's a pentagon. In the end, the object is a pentagon.
Yeah.
So we can draw pentagon in infinitely many ways. We can even draw it in a curvy
What do the
way.
mathematicians tell us? Is it a rationally embedded?
It's always a rational embedded. The slope is always plus or minus 1. That's the mathematics result. I will explain this construction. But yeah. So you could ask why plus minus 1 because it only comes from intersection of some chords with each other. So whether the 2 chords intersect clockwise or counterclockwise, that gives them the slope of the. So there is a lot of rigidity in their construction, and so this is the realization. This is now we are at this step of our program. Nothing to do with physics so far, where we are saying how to realize this associahedron in a Cartesian space. Now, what Cartesian space should we realize it in? So there is a natural Cartesian space that we can realize it in, which is the following: that if I look at this, if I look at the foregone, it is triangulated by 2 chords, 1, 3, and 2, 4. So let me label the 2 axes of my Cartesian space as x13 and x24. Similarly, if I look at the pentagon, I am, let's consider a 5-dimensional Cartesian space where each axis is labeled by xij. The ij are simply the internal chords. So ij's are 1, 3, 2, 4, 3, 5, 1, 4, and 2, 5. So we can always label our Cartesian coordinate with this. We can label our Cartesian coordinate system with these labels. Why? Because of the fact that each vertex corresponds to, this vertex corresponds to 1, 3, this vertex corresponds to 2, 4, like that. So it's natural to do this. And then for the 1-dimensional associahedron, this is the answer that mathematicians gave us, that that this realization that you get from this quiver theory is simply x13 plus x24 is some constant, positive constant. Drawing. Yeah, just drawing. So it's a representation. So at this stage, it's just a relation. And now we are drawing it as an object. Yeah. And similarly for the, in the case of this 2-dimensional associahedron, it becomes a little bit tricky that this is 5-dimensional Cartesian space. And we want to draw this 2-dimensional associahedron. And what the result of mathematicians say that there are 5 ways to do it. I'll give you one way, and one way is the following: that start with a preferred triangulation. So if I look at this combinatorial object, all triangulations are democratic because you can go from one to the other. But when you want to draw it, let's just start with one reference triangulation. So let's say we start with this, I'll call it T0. And then the realization of the associahedron given this reference triangulation is the following. It sits only inside a x13, x14 space and is the following shape, where this is x24 equal to 0. So I'm not writing the equation because there are too many. I'm just writing the boundaries. So it is as good as writing the equations. I apologize. x14 equal to 0, x13 equal to 0. And this is x24. So even though it's sitting inside the 5-dimensional plane, once I choose a reference, mathematicians tell us that it sits only inside this 2-dimensional space parameterized by x13 and x14. If you had chosen other reference, which is say 1, 3 and 3, 5, it would have set in the 1, 3, 3, 5 coordinate axis. So there are 5 possible realizations that we get of this associahedron. So again, so nothing to do with physics, but this is the output of the. So now you can ask, why are we doing all this? And the simple reason is the following, that our first question that we were asking, we had nothing to go by if you think about it. So we said that we start with the space Kn, which is the space of Mandelstam's. We want to classify functions which are S matrix of unitary local quantum field theory. If you do not put postulates like locality and unitarity, then this is an extremely bare object. Like it's just some ambient space parameterized by Sijs. And so there is nothing else that can guide us. So what we are doing now is that we are saying that let's try to find these shapes in this space, completely empty space, and let's see if there is something to do with S matrix. So I hope that the statement is clear that there is no other input except Poincare invariance. The only input we have used is from physics so far is Poincare invariance. Right? And because so this is some space which is coming from Poincare invariance when you have external particles with only momenta, scalar particles. And so far we have a completely divorced math construction which has morally something to do with Feynman diagrams, but nothing in concreteness. Now we will kind of join them together. So that is our completing this part of the program. By the way, even though this construction was put in from mathematical footing by, so I should name people who find this realization. So actually these are discovered first by physicists, Arkani Hamad, Wai, He, and Yoon. But then, they use some physics intuition to draw this, but these were put on this from mathematical footing regarding quivers, etc., by a series of mathematicians. I will not write all their names, but one reference is this is a paper that one of the papers, there were some others, which systematized NIMA and others construction on a form math footing. This was in 2019. Okay, so now the point is that we have, now let's think of right now Kn is just a space of Mandelstam, but now let's think of Kn as a Cartesian space. How can we do it? There is a nice way to do it, which is that instead of considering Sij variables, let me give you new variables which are the following. I'll explain why. So for all I less than j, let me define some variable which is linear combination of Mandelstam. So it's just some change of basis if you want. So once you know Xijs, you know Sijs and vice versa. You can go from one to the other by linear relation. But why am I considering Xijs? Because these have these have good intuitively good relationship with the abstract things we are drawing. Because if I consider actual scattering of particles which are arranged in a order plane like this, I'm looking at scattering of momenta P1, P2, and that goes into P3 and P4, for example. Then this chord, which I was calling small x13, is P1 plus P2 square, this propagator, which is same as capital X13. So, that's why we are introducing, instead of Sij, we are looking at these variables. Right? So, so far there is no input, no extra thing we have done. We just changed the basis because it has a nice combinatorial interpretation, these capital X variables.
So ordering is important. You have already ordered from P or
exactly. So here we are ordering now, actual ordering comes. So that's why we will get these planar amplitudes, and we will see how to go away from it. Yeah.
Why do we have to go to the realization step when we can just interpret Feynman diagram associated?
No. The point is, you forget Feynman diagrams. The point is that we are saying that we want to find functions in kinematic space which are S matrices of field theories. So Feynman diagram is a specific perturbative expansion of S matrix. So don't think about, Feynman diagram, I just said that, if you ask why am I thinking of these triangulations, am I going completely crazy? The reason in back of my mind is that they are dual to Feynman diagrams. But in entire thing, we are never using Feynman diagrams. Because what we get will be always the full S matrix. Some or all Feynman. We'll never get individual Feynman diagrams. Right. So these are combinatorial objects. If I just give you this anyway, I wouldn't know what the S matrix is. Right.
That's okay. But still, it does not give any motivation to study the realization.
Yeah, so far no, you will see the motivation in a minute. So far no motivation. So far we are saying we have, if you want two different Cartesian spaces, one is this just Cartesian space in which mathematicians are telling us how to draw, and one is our actual Mandelstam space. Okay, now I'm declaring the Mandelstam space a Cartesian space with capital X as my axis. So that's where I'm putting some input, extra input. Right? And so now it turns out that if you now say that if I just canonically identify, and this is extra input, nothing in mathematics telling us we do this, but suppose I just say that I am going to identify my Xij with Xij. Suppose I do this, then these polytopes directly sit inside the kinematic space. Right? In other words, I just draw it again.
J or J minus 1 or
J minus 1.
then J is I plus 1.
If J is I plus 1, it's just pi square. So it will be m square or a 0 or what. I mean, it's just.
That also means that vector.
No. That is just. Yeah, I should have said that. So this. Sorry. Yeah. So this is I. I less than. You're right. So this is mod J minus I greater than or equal to 2, and xi I plus 1 is no longer. Thanks a lot. Yeah. This is fixed. If mi square. Thank you. Yeah. Sorry, I missed that. Yeah.
That's why you have taken board, so X1.
Exactly. We never encounter in this small X space. We never encountered the. Yeah. So now, if I draw the one-dimensional associahedron by making this identification, I am insisting that this is where we are putting some input which has so far no natural math or physics basis yet, but its justification lie in the answer we get from here. So if I just draw this associahedron here, it just becomes this, which has the nice relation. So I'm just rewriting the same relation I wrote here. I just put x small x as capital X. And if you remember this, if you just see this x13 is p1 plus p2 square, as Ashok was asking. So this is S, our usual S variable, and this is t variable. And so this associahedron is kind of telling me that your u is minus c. Okay, that's what the math basically gave you, that you are finding a region in your Mandelstam space where your S and T are positive and your U is strictly negative and non-zero. Okay, if you make this identification. Okay. Now we are almost done in the sense that now this again there is a math result that once I give you this realization, there is a unique so if I give you this polytope of dimension 1, there is a unique form, then I can write down in the full Cartesian space, which is such that it has simple poles only on the boundaries of this polytope. So the details are, I will just write the result, it will become clear that given this associahedron sitting here, there is a unique form, unique up to some normal, unique up to sign, which has the same dimension as the dimension of the polytope. So one form, which is this is something maths people give us. Okay. What they will give us is d log small x13 minus d log small x24. But once I make this identification, I can rewrite it like this. Okay, and so this is fixed up to a sign.
The normalization is also fixed.
Normalization is fixed up to a sign. It's just plus or minus 1. And so this is a form that is given in this full space. And now let's look at the restriction of this form on the polytope itself, which is this equation. So I just write it quickly. So what we get is 1 by x13, which is S, plus 1 by x24, which is t times dx. And so this is the restriction of the form on the associahedron itself, okay, which we have drawn here. And now you can notice what this is. This is just the planar 4-point amplitude for a scalar field theory. So that's a remarkable surprise so far. that this is something that came from math. And if I use this as the extra input, and this is what we are going to exploit, which is where we will come to the many realizations. Many realizations will be looking at all possible mappings between the small x space and capital X space. But if I give the simplest mapping between the two, between the Cartesian space and the kinematic space, then I get this S matrix.
And does it matter what variable you use to parameterize the associated? Because you could have used x2. In this case, it will just change the sign.
Yeah.
It's a bx1, suppose you take bx2, right?
Yeah.
The overall sign will change.
Yeah. It will always change up to a sign.
It will always
Up to a the way it's yeah.
That's the extra factor.
Yeah. If you are consistent that what you are calling x13, I mean x13 could be called x24, but non-intersecting chords should be go to non-intersecting chords. Like 13 goes to 24, 24 goes to 35. I think that's what you are saying, right? Then it will only change the sign. Is that what you are asking? Yeah.
I'm just saying a more complicated situation, right? If you have a higher dimensional form, if
Yeah.
you have a n form,
Yeah.
3 dimensions.
Yeah.
You can write in terms of very different ways coordinates, right?
Well, so here I'm saying that we are given we have fixed small x Cartesian space once and for all. In that we drew we had to fix this for the mathematicians to give us how to draw this. Once it is drawn, there's a unique form we write in this, which is such that it has simple poles only on the boundaries of this polytope. So so this form, if I had put
That point
yeah, okay.
Now the point is how you parameterize this line. Which coordinate you use to parameterize this line?
Yeah, so you're saying in the capital X. You are talking about the capital X. No, you are saying that what if this was x24? Yeah, doesn't change anything because the whole thing will be up to a sign. It will remain the same. Yeah, we can check that. I will come to that. I will explain to more generally. Yeah, I'll give you the result more generally. Yeah. I understood the question. I think now. So let's look at the same idea for the two-dimensional associated. Sorry, how much time I have? You have to tell me.
How much time do you need?
No, you tell me. Then I'll wrap up fast.
10 minutes, 15 minutes?
Yeah. Yeah. No, that minus sign came because of the this is a gift of mathematics again, that given a positive geometry, any positive geometry, not linear or anything, there is a unique form you can write in the space in which you are describing a positive geometry. There is a formula for it. That formula, when you do it for the simple case, it gives you this.
For example, if you had x13 minus x24 equal to c,
then we won't get S matrix. I mean, if that was what mathematics gave us, we would not get S matrix. Yeah. I was that's related to Ashok's question. I was about to write that. So let me write for the
suppose you parameterize this line
with x24.
Yeah, as x, no, not x. As x13 equal to 2u and x24 equal to c minus 2.
Okay.
And write it down to d. Right?
Well, I mean, so you have d. So you have dx13 by x13 minus dx24 by x24. Now what?
I'm just saying, right? Parameterize this line by x13 equal to 2u.
Okay.
And x24 equal to c minus 2.
Okay. So then, so this, so d, I mean, whatever way you parameterize, dx13 will become minus dx24.
So that,
yeah.
Inside the square bracket, it will be 5.
So you will have 1 by x13. Okay, sorry.
dx12 will now become d2u, right?
2du. Yes.
Right?
Yes.
So that fact that you have to remove that 2.
No, but that's what that's what I'm saying, that once I fix my Cartesian basis in the small x space, the form that I'm getting is with where the parameterization in this case is either d small x13 or d small x24. So I was writing more general formula now. Yeah. So you are asking that here, there is no, you cannot do, this is not the canonical form. Yeah. It's not allowed for the small x basis. Yeah, you could ask what if I had a capital, then you would say that I'm getting a theory where the coupling is to, I mean, So let me give the more general result as Ashok is saying. So let's look at the n equal to 5, where we have a two-dimensional associahedron.
Alok? Hello? Hello?
Anish, yeah.
Yeah, in the case where you have this massive particles, does the thing extend for one loop as well?
Yeah, I'll come to that. Yeah. You have a single mass?
A single, let's say you just have
Mass
one
is
type of
trivial.
field.
I mean, we just label xij by xij minus m square. So it doesn't change anything.
So now if I now allow the mass to be negative, like tachyonic?
Mass to be?
Negative, does what breaks down? Like by...
Oh, yeah. What will break down is that the geometry will not sit inside the positive space, positive quadrant always, right?
I see. Okay.
So there is definitely a distinction between positive and negative m square. I mean m square, not m. I mean m could be, because we are only getting m square, right?
Right.
So yeah, you are saying m square negative.
Yes, tachyonic.
Yeah, that will shoot the polytope in a different quadrant. I mean, so we can talk about that. Yeah.
Okay. The reason I asked that question was because unitarity is sort of baked into the structure of the positive geometry, right?
In the structure of the form, yeah.
Yeah. So, and it should certainly not allow for that kind of an extension that you have tachyonic sort of theories.
Yeah, it will not allow. I agree. So it will not allow. I mean, if I have time, I will tell you that if you had, say, for example, negative lamp coupling in the, then it will make this concave polytopes. We will not get the things break down in some very specific way.
I see. Okay.
Yeah. So either yeah. So related to Ashok's question, so let me just again say that remember that for two-dimensional association we have to choose a reference, and we chose it to be 1, 3, and 1, 4 just for convenience, and we got this kind of a shape. And then this is the associator drawn with a reference triangulation which is 1, 3, 1, 4. You could draw it with any other reference. It will be in some other plane then. And now if you write the form, the unique form that you get from here, that is sorry. So the rule for writing this form is very easy. Every time you do one flip of a diagonal, you change a sign. So if you change, that is, I unfortunately erased the shape. So this term is associated with the topmost vertex, which was the triangulation 1, 3, 1, 4. If you change 1, 3 to 2, 4, then this you get d log x24, which d log x14. And because you only change one diagonal, you change one sign. So that's the rule to write this formula. I mean, that's kind of the algorithm. So you'll have 5 terms. I won't write all of them. And now to answer Ashok's question, now when you pull it back onto this, so this is a form which is in the full space, full 5-dimensional space. It's a 2-dimensional form in a 5-dimensional space. If you pull it back onto this associahedron, then you get so this is these are the basis that parameterizes, and that's dictated by what reference I choose to draw it. So because it is sitting in this space, the form that multiplies this function is this one. So even if I change the reference, this function won't change, but this basis will change. So that's like a gauge, pure gauge transformation. And
always have to write it.
Yeah, exactly. So now there is a different, I don't have time, otherwise this has interesting connection with the color factors in the scale theories with color. But if you just focus on this guy now, then again this is a planar 5-point amplitude for 5-cube theory. If I identify xij with xij. So this is one point that I wanted to insist, that up to this point it's all math and nothing tells you this is S matrix of what theory. But once I do this identification, then it gives me a specific S matrix of a specific theory. And now what we want to do is we want to exploit this. So this is this is an identity diffeomorphism between the Cartesian space and the kinematic space. So we want to now look at all possible diffeomorphism and see that what class of diffeomorphism give us S matrices. Okay, that's our goal now. And so to begin with, we can start with linear diffeomorphisms, and we get interesting results. So I'll just explain 5 minutes now. Okay, I'll explain some interesting thing we get with linear maps. So I hope that now the thing is clear that it's unique. So with your lack of time, I'm only giving you associahedron. But you take any positive geometry, there is a unique form. Yeah.
So since you're in a country, it's probably a silly question, but since you're in a country, there is a unique tree form also, right? By partial. Does that tell you something about the physics? Does that tell you something?
No, you're right. I haven't thought about this. I mean, no, you are right. It's a good question. I don't know if that. I mean, it has same information as this, but you are asking what.
Yeah, I mean, does that say anything about the
Yeah, that's a very good question. I don't know. I mean, of course, it gives us the S matrix for the same reason this gives, but you're saying something more. Does it give anything more? Yeah, I don't know. I haven't thought about that. That's a yeah. That's a good question. So I will give you one. So okay. So now we are saying that okay, we have this abstract space. I didn't give you the counting, but space of the dimension of Mandelstam invariance is this one. All the all the small xi's if you count, the total number of ij's, total number of chords you can draw in an n-gon. That's just like that's just this number. So this is the space in which mathematicians told us how to draw the associahedron, and then we have the kinematic space, which also has the same dimension. And now we saw that if you take just identity map between the two, then you got the S matrix of planar scalar theories. And so we can now start exploiting other realizations, that is exploiting other diffeomorphisms. So we can start with the simplest ones, which are linear, of course. And so I give you the simplest example. So let's consider a map of the following type. So let me just call it F, which is a map that is such that my xij is equal to, it's parameterized by some permutation, is p sigma I plus p sigma I plus 1 plus p sigma j minus 1 the whole square. So I could look at, I could fix a permutation and I could look at maps like this. So just to give a simple example in n equal to 4 because of lack of time, suppose you consider, so we have x13 and x24 on one hand, and the simplest identity map we saw was x13 equal to x13n. Now what I'm telling you is that suppose I consider a non-trivial permutation which takes 1 2 3 4 to 2 1 3 4, then I have the x13 is still x13, but my x24 is x24 is p1 plus p3 square. I'm giving a map between these two spaces. A linear map. The coordinates are fixed on both. Here the coordinate is x13, x24. Here the coordinate is capital X13 capital. That's fixed. Yeah.
But in terms of particles, you permutate the particles.
Exactly. I'm just giving a simple map as an example. You're right. We're just permuting particles. Now we can ask that. So if I choose this as my map, if I choose identity map, this associahedra sat here. If I choose this map, what will be the image of this associahedra in this space? And that you can easily determine. It's simply this one. So the map, the image of this associahedra with this map is simply which is t equal to minus c, or x24 equal to minus c. X24 equal to minus c. If I to choose other sigma, which was, so there are, of course, this is 4 particles. So up to cyclic permutation, you only have one more choice, which is If you choose this as the sigma, and again you write this map, then you will get the ABHY realization in small x space gets mapped to this one, which is so this class of maps gave us 3 realizations. One, the one that is obtained from identity, which gave us the planar S matrix for phi cube theory, and we get 2 more. And now you can immediately see that if I now pull back the form on this, this, and this, that is, once I have a diffeomorphism, I can just push forward the form, and I add, then what I get is you just add the 3 forms, for example. So there is a way to add it. This is related to earlier asked question, Siddhartha, how do you add these geometries?
But individually, they don't give anything.
So individually, this is giving me, exactly, this gave me the planar, this is giving me planar phi cube, but the ordering is switched of the particles to 1, 3, 2, 4. And this is the giving me the planar S matrix where the other ordering is fixed. So if you add, I just get up to a factor of 2, 1 by S plus 1 by T plus 1 by, which means that if I add and I just divide by half, at least in this trivial case, then I'm getting the tree level S matrix for ordinary phi cube theory, not with color or anything. And what is interesting is that this can be proved to any n, that there's a nice formula, which I will just write and maybe end with that, which is that.
Is it clear that if you make any diffeomorphism in the X space?
Yeah.
That gives an S matrix.
That's our goal to see. So, so right now we start with a very trivial diffeomorphism, and it gives something interesting. Now I will give you slightly more general linear diffeomorphisms, and that gives S matrix for this other phi 1 cube plus phi 1 square phi 2 theories.
But suppose you make it arbitrary.
Exactly, and whether that gives this derivative theory, that's what we want to understand. I think generic diffeomorphisms probably don't give anything sensible, is my feeling. But if I look at, so far what we have found is that any linear diffeomorphism is giving us S matrix of some local unitary theory, and the question is whether if you have nonlinear diffeomorphisms, what that is. So let me just write the answer of for the, so this was already like a very dumb diffeomorphism, but it already gave a nice little answer that which kind of answer one in some sense criticism of this program that we always get planar S matrix, but that is just because we studied one realization. If we studied all of them that math gives us, then we get not just get planar S matrix. And the final answer is the following, that you just consider sum over all diffeomorphisms, and you push forward the form that we have in the abstract Cartesian space, and now you just divide it. It's very, very simple. You just divide it by this number. So this is because of some beautiful combinatorics that works out, and this is the endpoint amplitude for ordinary phi cube theory with particles without color. So
This you couldn't have gotten, suppose you knew the color order dimension.
yeah,
From that you can reconstruct the.
certainly. But here what we are saying is that reconstruction, what it would amount to is that I don't look at a fixed Cartesian space. I look at x13, x24 as an orthogonal coordinate system, or I look at x13, s13 as an orthogonal coordinate system, and I realize in different ones and add. But now we are saying no, we have fixed ones and for all our ortho. So S and T are orthogonal, but S and U are not orthogonal. So that's so we are not changing the spaces given to us. We are just fixing them. Yeah, but it's not a big deal. I'm just saying it just come out nicely. Yeah. Sorry. Yeah, they are actually technically. I'm being a bit sketchy. They are what are called right cosets of the dihedral group. So you have to mod out cyclic permutations and also permutations which are. I mean, just because you ask. I mean, but I didn't go into all these details. Suppose I give you a permutation which map this ordering to. Then this as you can imagine that every planar, every propagator is going to same. The set of propagators don't change. So I have to those I have to quotient out. That's why I'm writing the square bracket here. So there is a specific coset group that one has to sum over, but that is easy to understand. Just cyclic permutation and these ones you quotient out. But what was interesting was that you get a very. It's not like you have different coefficients when you add. You have it has a very simple, yeah. Okay, yeah. And now just to give an example of the, if I consider the following diffeomorphism, which is xij equal to alpha ij xij, let's say minus mij square. And if I consider the such that alpha ij is 1 if okay, let me, sorry, I have to say. So now I'm giving you a more general diffeomorphism, which is not permutation. It is not like permuting ij. It's just doing some linear. It's a diagonal map between small x and capital X. So the one that we looked at before was right. The one that we looked before was x13, x24 was some 1 0 something like minus 1 0 x13 x24 some off diagonal matrix. Now I'm saying let's look at other class where it's diagonal, but the coefficients are arbitrary numbers, not plus or minus 1. And then it turns out that if I consider, so I'll just give a final result that fix some ij, fix some pair ij, and now you consider all possible xij's, or consider all possible pairs mn which belong to, sorry, this is a little technical, but I'll just end with this result, which belong to I, go all the way from ij to I plus mod j minus I minus 1, j plus mod j minus I minus 1. Let's call this set of all such mn, let's call this Sij. Okay, so I'm introducing some set just to repeat. Fix some ij and look at the set of all chords where mn belongs to this range, and now I give you some map. So choose xij equal to alpha xij. Let me forget the mass also for a minute. Alpha xij for all ij in S. Maybe I should call it mn, sorry. And is equal to xmn otherwise. If I choose this as a map, and then I do the same procedure, I just map the associahedron into the Cartesian space, then you can see the slopes will change. They will no longer be 45 degrees or plus or minus 1. They will depend on alpha, which is related to.
Find the set A7 for every MN.
For every MNN.
And now you are saying that X7.
So for this is a map parameterized by ij. I fix ij. For each ij, I introduce a set, and wherever mn belongs to that Sij, I do this map. And if mn, so this map is parameterized by each pair ij.
Ij is not the set. Ij is the.
I say just label. Yeah. So let me call it ij is some label. For each ij, I have a diffeomorphism, which is defined like this. Why am I doing this? Because I have a specific. I'm asking an inverse question. Now, given a Lagrangian, is there a positive geometry? The Lagrangian was, what I wrote down earlier, which related what Sid was asking. So, if the Lagrangian was, just to repeat, it was partial mu phi 1. Let me ignore all the masses for simplicity. I equal to 1 to 2 minus lambda 1 phi 1 cube minus lambda 2 phi 1 square phi 2. Lambda 1, lambda 2 are arbitrary. So now the question I'm asking is there a positive geometry for amplitude of this theory? And the question is that if I use this map, then you can show that, okay, so I will just write it down. If you sum over all the f's, I'm writing it formally now, then, and if push forward the form, then this quantity gives you the amplitude of this theory up to order lambda 2 square if alpha is lambda 1 square by lambda 2 square. Sum over all f means sum over all ij's basically. Yeah. So it's a very simple formula. You just do this and you get the perturbative amplitude of this up to order lambda 2 square if alpha is lambda 1 square by lambda 2 square. So so now I gave you just two example, one where we,
Give the answer. given any Lagrangian, can you systematically go back?
Yeah, we don't know that yet. I mean, if you give me random Lagrangian, I don't know.
So take cubic Lagrangian.
Without higher derivative terms.
No higher.
Yeah.
No higher. Just cubic Lagrangian, arbitrary cubic Lagrangian, right? In this case, it will be lambda 1, lambda 2, lambda 3, lambda.
Yeah.
And is it possible to systematically go back?
Yeah, I hope so, but we haven't looked at for all of them. So the reason we looked at this one was the following, just to give a motivation. I mean, the reason we looked at this Lagrangian specifically is because we took phi 2 to be massive, and then you got and if you look at the amplitude up to order lambda 2 square, means you have one massive propagator. And now if you integrate out the massive degree of freedom, you get the theory with a phi 1 cube and a phi 1 4 coupling. And we showed that in the geometric picture, that means the associahedron runs to infinity, and it looks from finite region in Mandelson space. It looks like a low dimensional polytope, which is this accordiahedra that I said in the beginning. So there was a context for which we look at this one, but in general, you are right. We could look at more general thing, and I don't know whether we will find diffeomorphism. It's not clear. Yeah. Yeah. Okay. Maybe I should stop here. So the main point is that I didn't have a time, but so far I've just told you how to map. This is the first part of the story. So I ran out of time. I just gave you some evidence that how this leads to a large class of tree-level asymmetries. If you just project out this associahedron in any of these boundaries and then restrict the form, they always seem to give us some amplitude for phi to the k theories. So if you combine both of these operations, then you get a large class of scalar field theory tree-level amplitudes. So maybe I stop here.
I mean, in this case, we are only taking this kind of planar and we are triangulating. That's why we are getting phi. If you take higher dimension version, we might get phi to the power 4 or 5.
No, so the phi to the 4 comes just from here. The point is that if you restrict this associahedron to any of these low dimensional faces, because we know that every phi 4 pole is always it's a subset of phi cube poles. But that doesn't mean that if you do this you will always get, but it's just true that if you project onto any face, you always get an amplitude for some phi to the p higher theory, and a specific of those projections give to phi to the 4 amplitudes. So everything comes from here.
Do we know something if it is a more generalization version of associahedron and triangulation? Do we know what we get?
No, we don't. No, that's a great question. I mean, you are saying that you're saying just go beyond, related to maybe what Ashok was asking, go beyond dissecting polygons. You're saying dissect some three-dimensional. Yeah, I don't know whether we understand what those geometries are, but we don't know whether they play a role right now in physics. So I mean, the amplitude and we understand n equal to 4 super Young-Mills, but ordinary Young-Mills, no, we don't know what the geometry is, which is tied to the fact that so far, if you notice all the forms we are getting, they have no numerator factors, right? I mean, I erase it. Like it was like 1 by x13 plus 1 by x24, etc. So it's related to Ashok's question also, that whether, and our hope is that maybe there is some nonlinear diffeomorphism, which would give us appropriate numerator factors for high derivative theories, scalar theories, or Young-Mills theory, for example. So I know Nima has some work, but it's not published, where he has shown how to map gluon amplitudes from associahedra by what people do, spinning up Witten diagram, that kind of technique, but it's not out yet, so I don't know exactly what. There is a relation of thinking out associahedron and getting some gluon qualities, what I understand, but yeah. Yeah.
Can I think of them like, instead of taking this 45-degree like this canonical?
Yeah. Exactly. So if you slope, if you relate to what question Anish was asking earlier, so if you change this, you're changing a slope. And what is interesting is that it will always remain a convex polytope as long as your couplings are positive. So if you become negative, then it will become concave, and that's interesting also, because it kind of tells you that we know that if you have a lambda phi cube theory with a negative lambda, then it will be some Sikh theory in a EFT context. So
if you do a nonlinear diffeomorphism, that's like coming this line.
yeah, so one nonlinear diffeomorphism we know, I didn't have time, which is the, if you consider, maybe since you're asking, I will spend few minutes to explain. So there is something called CHY formula, which is this worldsheet formula for QFT amplitudes. And that formula is of the following type, that there is this, there is some moduli space of n punctures on a Riemann sphere, and then you integrate some form on it, like a top form, for example. But you don't integrate over all of this, you have to localize it on some points which are solution to what are called scattering equations. So this is some abstract formula. Now this moduli space, if you compactify, that is an associahedron. And then, so you have an associahedron with a form which is giving you, and if I choose this omega 0 and to be the top form, it gives phi cube planar phi cube amplitude. So you have a planar phi cube amplitude coming from this form on this associahedron, and you have planar phi cube amplitude coming from the kinematic space associahedron. And so this is the example, and when it has been proved by Nima and others that this is in fact a diffeomorphism from this associahedron to the kinematic space associahedron. So this is a nonlinear diffeomorphism we already know, which it doesn't give us a different theory, it just expresses the amplitude in the same theory in different coordinate charts if you want.
Do soft theorems somehow relate and associate?
So the one interesting point was that in the associahedron case, if you take nth particle to soft, then when you are evaluating the form, top form, it is like evaluating volume of a dual geometry. If you take one particle soft, then you are going to one lower dimensional polytope, and its volume vanishes, and so you get this soft, this Adler zero type soft theorem, which are perturbatively you can check, but they are very hard to check. So you do get soft theorem, vanishing soft theorem from in the phi cube theory from the associahedron. But in general, I don't know, because we don't know how to write gauge theories. So in general, I don't know how to relate the geometries for the n amplitude and n plus 1 amplitude and soft theorem. Yeah, because here soft theorem has, like, they just vanished, amplitude vanished in the phi cube theory. So which is captured by this thing. So I will just say one thing since you asked that. What we now realize was that this in CHY it was always hard to. It was not known for, as far as I understand, a long time, that if I give you this kind of class of theories phi 1 cube plus phi 1 square phi 2, and if I want to look at the scattering of say phi 1 particles which are massless, what is the CHY formula? But now we understand it very trivially, which is just write this Sij instead of Sij, you write it in terms of first Xij as a linear combination, and think of this Xij as actually Xij. So as you vary x in terms of alpha, but don't change the form, that's the CHY formula for this lambda 1 phi 1 cube plus lambda 2 phi 1 square phi 2 amplitude. Yeah, with phi 1 external particles. So the form doesn't change, the geometry doesn't change, but the equation get deformed because the diffeomorphism is getting deformed. So yeah. Right, thank you. No, I think it's.
Okay, if not, let's thank Alok again.
Thank you.